Hello, this is Dr. Marion Carroll, and this is General Chemistry at South Central Louisiana Technical College. We've been covering a lot of the basic principles in general chemistry, and this final topic that we've come to is essentially concerned with equilibrium. And I'll also include acid-base chemistry as well, where I think we're looking at lecture number 11. So we'll look at equilibrium, and then also equilibrium as it concerns acid-base chemistry and some other applications. So most of equilibrium in the word implies that we have equal parts, and we'll talk about chemical equilibrium, but if we look at physical equilibrium as an example, if we take a vessel, if you have like a beaker, and in this beaker you put a lid on it, or a cap that's sealed, and there is an inlet for adding gas or increasing pressure, and another inlet that might be closed. So in this vessel we have a solution, water, and at room temperature, or let's say standard temperature and pressure, we're going to allow an equilibrium to take place between the water, or the liquid, and the space above it. What will happen is that the liquid will evaporate. There is a certain effort that molecules in water put forth to come out into the atmosphere, and it is directly proportional to the pressure that is placed on that liquid in the atmosphere. So because you have a low concentration of water here in the space above the liquid, and obviously a high concentration of water here, the water vapor that is released will equilibrate with the space that's empty above the water. So what we'll end up doing is you'll have some condensation on the glass that will develop over time, and of course as molecules rise, this is referred to as evaporation. So we have a equilibrium, physical, between the evaporation and the condensation. Of course, as the vapor gets higher in concentration in space, it will condense on the surface of the glass and kind of roll back down into the liquid. Now, if we add pressure to this vessel, we increase the pressure of the atmosphere inside this vessel. Same amount of liquid, same space, but we raise the pressure. If we raise the pressure, then we reduce the ability of this water vapor to form. So these are the larger arrows up here at the top. Smaller arrows, meaning the evaporation takes place at a lot slower rate, or a less of a rate, but eventually you will get an equilibrium, because the condensation, although is less because of the less evaporation, you will eventually recover back to this original equilibrium under different pressure conditions. So we increase the pressure, we're going to reduce the evaporation, but the condensation will continue. But of course it will be less until we reach a point where the evaporation and the condensation equal each other. And at this point it will be at a higher pressure, okay, when it returns to its equilibrium. So all this is kind of set up the concept of a chemical equilibrium. A chemical equilibrium works in the same way. If we use a general expression of A plus B, and get my plug in here, about to lose power. Okay, if we use the general expression A plus B goes to the products C plus D. Alright, so these are my reactants, these are my products. If if this was a reaction, and many reactions are, that is capable of going in the other direction. In other words, the products now become the reactants, and the reactants initially become the products. Alright, many chemical reactions are capable of the reversibility. And so this equilibrium that forms between A and B and C and D occur at a value that we call K, or KEQ for the equilibrium. And KEQ is equal to the product. In other words, you multiply the concentrations of the product and divide it by the product of the reactant concentrations. Alright, this is the expression for equilibrium for every chemical reaction. And the typical concentration unit is molarity. Okay, there are other concentration units, but typically the expression is in molarity, that is, your molecules are in solution. Molarity is equivalent to moles per liter with the symbol big M. So equilibrium in a chemical expression can be determined for chemical reactions, and this is a constant, K being a capital letter signifying constant, because the concentrations of our products are determined by the concentrations of our reactants. These concentrations will change if we change concentration of our reactants. And of course, the product concentrations will change. Reactant concentrations will change if we change the concentrations of our product. So all of these factor into this constant. And we're going to look at some actual examples in a minute. K can be calculated by taking the products of the reactants and the product of the products of a chemical reaction. If one or the other of these changes, it will change the value for the constant only temporarily, because just like in the case of the evaporation and condensation, this temporary change will then return to the value of the constant if once the reaction reaches equilibrium. And an equilibrium constant is unique for the reaction because the ability of these molecules to interact with each other and to form the products is constant unless you change one of these reactants to a different reactant. Unless those are changed, the equilibrium constant will remain the same. So let's look at an example. You have a reaction, nitrogen plus hydrogen gives us ammonia. It's in equilibrium, and we don't know what that equilibrium value is, but we can determine that if we know a few other things. For instance, if pick some arbitrary numbers. See if I can find some nice values here. Alright, let's just use these. So, the expression, equilibrium, is concentration of products over the concentration of products over the reactants. I have nitrogen at 6 molar. I will have hydrogen at, let's say, 5 molar. And the concentration of my product, ammonia, is, what could it be? Let's make it 9 molar. Alright, so what's the equilibrium? Well, the first thing in every chemical reaction you must do is balance the equation. And so in order to balance this equation, I'm going to need 2 moles of hydrogen, give me 6, and 2 moles of ammonia, 3. 3 moles of hydrogen, give me 6. 2 times 3, and then I have 6 moles of hydrogen over here, 2 moles of nitrogen, 2 moles of nitrogen. And you already know that 1 is assumed to be in front of the nitrogen. So with a balanced equation, my expression for the equilibrium looks like this. Concentration of our reactants, nitrogen, N2, times the concentration of our hydrogen. And because we have a coefficient of 3, this is the exponent of that concentration value. And then divided by the concentration of our product, it too has a coefficient of 2. And so we place our values in. We'll say 6 molar times 5 molar squared divided by 9 molar squared, 5 molar cubed. Okay, so that's 6, see, 5 times 5 is 120, is 25 times 5 is 125. So that'll be 6 times 125, which is 5 cubed, divided by 81, which is 9 cubed. And let's see, need to do the math real quick. But 6 times 125 divided by 8 will give us our KEQ. Here's my trusty calculator. Okay, so 6 times 125 equals 750 divided by 81. 9.26. This is our equilibrium value. Sometimes they're units, sometimes they're not. This will be in molar. Actually, this is molar. 6 is in molar, 5 is in molar, 9 is molar. So we'll have molar squared. We'll have 6 mole times 3, so that'll be, this is mole to the 4th. So 2 of these cancel. So our answer is in mole squared. Alright, so this is an example of calculating equilibrium from a reaction. And so we'll look at another practical application of this in terms of acid-base chemistry. So thanks for listening, and stay tuned for Part 2.